So again, the idea is I'll record the lectures, but this is not broadcasting time. So if you have to miss a class or you want to go back, you can listen to this. We're not doing hybrid because that was way too hard as a class, right? So hopefully you can make it, be here. If not, this is available to you, right? Okay, so this class will be about, data science for power systems. And so today we'll do a sort of introduction and review, and we'll get into sort of the meat of the class starting next week. Okay. So a little bit about me, right? So my name is Balson. I think some of you know me, some of you may not. So I've been here for about 7.5 years. My research is mostly on control, optimization, and I do quite a bit of machine learning for power systems. So, some topic you see in this class is related to what I do. And some of the techniques has been applied by folks like Seattle City Light, Microsoft, Centrica, and people like that. So I'll try to introduce some sort of more practical data that we will see in this class. Right? So hopefully, I may not be giving you the real data, but some data that looks like the real data you will see in practice. Right? Hopefully you'll get something like this. So how to contact me, right? So my office is upstairs. I'm 310. I will have an office hour on Mondays from 3:30 to 4:30. Now, in my past experience, you will need, or some people will need some help, especially once we get into the programming part of the class. So I do encourage to come to the office hour if you're able to. If you're not able to make it, email me. I can find other times to work with you. Okay. So just for me to get a background shorthand, who here sort of hasn't really programmed in Python, let's say, before? So we all know Python. Who has not? Who has not worked in Python? So we all know how to manipulate matrices. We know how to plot, things like that in Python. Okay, good. Right. So so those are some of the basic skills we require. And in this class, we'll use sort of Jupyter notebooks, right? So all your homework, most of your homework will be essentially on a notebook. I'll give you some data, you try to do something with the data, and that what the homework look like. Okay. But another background then here for the folks here, who does not have experience with power systems? So who does not know how power systems work? So the rest of you are familiar with power systems? Okay, so somebody tell me what reactive power is. What is reactive power? No, all right, so yeah, let's be honest, let's try again, right? So who does not know what reactive power is? And for the rest folks who did not raise their hand, I'm gonna assume you know, right? Okay, so here in this class, it's a mixture of both sides, right? So it's data science, but we're teaching enough power systems, right? So it's hard, sometimes hard for me to gauge this. So if I go too fast or too slow, just let me know, right? So, I'm telling something you already know, or I'm saying something which I assume is well known, but you have never heard of it, just let me know. Okay, right? So people come from sort of wide backgrounds. Okay, so textbook, there'll be no textbook. There's really no good textbook for those kind of classes. We'll pull from all types of different sources, right? Really sort of, teaching power systems or basics. There's many textbooks on that, but they're not something you can learn in a few weeks. So I'll be trying to extract material from there. Now for the data science side, for the programming side, again, there's really not a textbook that works, right? So we'll go through, sort of teach some of the basics, do some exercise, and go alternate like that, right? So there's really not a reference. So the idea is we'll have sort of weekly homework that's to do those. Those really will be your reference going forward. Okay, again, you have trouble with homework, just let me know and we can work through that. Right, so class format, again, It's recorded and it will be uploaded to YouTube later. And please interact if you guys want. So at 6, we start at 6. If there's no questions, we'll finish by 7:30. I'm okay with that, right? I'm happy with that. We got to go home at 7:30. I'm happy to go home at 7:30. But you're paying money for this, so if you have a question, just ask a question. Okay. No, not react, like interact, right? If you have questions, just ask in class, right? Don't sit there and say, listen to me talk for an hour and a half. Okay. Again, I'm happy we finish by 7, right? Okay, but let's try not to finish class very early. Okay. So this is the website. Again, this is the main course website. You should all have received email from me about this course website, right? So everything will be posted there. We'll use GitHub, but that's public, right? So basically everything is from this website. Canvas, we're only going to use for grading purposes. And when you sign on to the Jupyter Notebook, you need to sign in use Canvas. That's sort of the only thing we use Canvas for, right? Just our logging system to the notebooks, and then for grading purposes and homework submission. Okay, grading. So we'll have homeworks, almost weekly homeworks, right? So about one every week. We have a final project. Right? So for you to try out the techniques we talked about in this course, for some in this class, for a bigger project. So a project can be a team. And if you can't find a team, that's okay, right? So the grading will take into account how many people is in a team. Right? A team with 3 people, you're expected to do more than the individual personality. Any questions about the system, about the grading system? Okay, and for the project, there's enough open data now. There's enough open source data there. You should be able to do a project on whatever topic you're interested in. So this was different. This course was first offered maybe 4 or 5 years ago. It was actually really hard to find data in energy systems. Nowadays, we have exponentially more data. So you can find data on whatever you're interested in. There'll be some kind of data out there. Either it's real data or synthetic data, but on almost everything that you're interested in, there'll be some data. So you can, there's final project really not that restricted, right? For anything related to the classwork. Other questions? Okay. All right, so programming, again, there'll be lots of programming, right? Homework will be sort of some things you write down, some things you do on a notebook. Try to do homework early, especially towards the end of class. There will be a lot of just programming issues that comes up, right? So we'll be loading all kinds of packages in notebooks. Sometimes it just don't work. Okay, so you want to try it early so that I can debug it, right? I can help you debug. Okay, you don't want to, so all the homeworks are not terribly difficult to do, but the problem is you wait too long until the end. Then if some packages goes wrong, you can install some packages, then right, sometimes that takes some time to debug. Okay, so try them early. Try homework early. Okay, any questions about the logistics of the class? Yeah. Yeah, we'll use Jupyter Notebook. We'll use Jupyter Hub exclusively. We use Jupyter Hub exclusively. So if you go on the course website, you see a link for Jupyter Hub notebooks. Each of you will have individual workspace. I can see your workspace. So the homework will basically for you to create a notebook in your workspace, and I'll grade just that notebook. Okay, so this is, the good thing about that is it's version controlled. So everything that works for me should work for you. So in the past, we allowed different type of programming language. Debugging was a nightmare, right? And doing version control is a nightmare. Just how will you ever submit that is also challenging. So this time we're gonna do Jupyter Hub. And the homework will be a bunch of questions. You create a notebook that finish all those questions. I'll just I have access to all your workspace. I'll just log in and look at what you have done. Okay, and this way it's timestamped. I can see what you're doing. Okay, so this is a much easier process. Who here, I guess, are you guys familiar with Jupyter Hub? Are you guys familiar with notebooks, right? We know what Jupyter notebooks are. No, okay. Good. So the first homework will be that actually. We'll be logging into it, make sure it works for you, and you can follow an example that I have created. Right? So I haven't posted homework yet, I'll post that tomorrow. That'll be the first homework. It's actually not very hard to use. Like all the hard things are done by UW-IT at the backend. So what you should be able to do is just go there, type in your UW login, you see this environment come up, you can follow that notebook and recreate that. It should be very seamless process. Again, if that doesn't work, we'll figure out soon enough. We'll find out soon enough in the first week. But that's the idea. That's how we're gonna do it. Yeah. So yeah, so all the code we'll be writing is basically we're writing Python. We're writing Python code. We're just writing Python code, except that it's in a control environment that I have full control. I can see what's going on. And so if I can try out the homework questions, again, they work for me, they should work for you. We should not have sort of weird, whatever version Python you're running, those kind of issues, right? We try to avoid those. Other questions? Good. Yeah. It doesn't matter what you use, right? It's web-based. So you're running, UW-IT is running it. So we're running on the UW cloud. You're basically just interacting. Sorry? Linux. A LaTeX. Do I expect LaTeX for your homework? Right. I don't expect you to write in LaTeX. If there are pen and paper questions, you can write it on a piece of paper, take a picture. I'm perfectly fine with that. Right? If you want to type LaTeX, you can do LaTeX. Yeah, so it's totally up to you, right? As long as you're handling the homework in some way. No, I don't expect LaTeX is a little bit too much, I think. Some of the questions are pretty easy to do, but take you a while to type it out. Okay, yeah, so although I do expect when you ask to plot something, it's a computer-generated plot, not a plot by hand, right? Not like I plot this by hand, it looks like this. But there's no TA for this class. We missed a cutoff by 2 people. Yeah, I can answer a question on weekend. Not immediately, right? Not immediately, but I'll try to answer within a day. I'll try to answer your question within a day. Also, I guess on your side is try to make the question something that has a short answer, right? Not what should I do about problem 1, right? That's really not a good question, right? As, a better question is for homework is for problem 1, I'm trying this. Do you think it's right? And this kind of. And previously we had TAs, but most of the time TA spent was actually debugging Python. Right? That was 80% of the TA time was spent on that. So hopefully by moving to the sort of version control Jupyter Hub, we can avoid doing that, which makes the things much more smooth. Okay. Any other questions about homework? Okay, all right, so good. So let's look at the course, right? So, why use data science or machine learning power systems, right? I guess in some extent, this is the question that we're trying to answer throughout the course, actually. So the whole course is giving a feeling of what are the questions that can be answered by learning or machine learning. What are the questions that, how do you combine basically your system knowledge and learning, I guess, there's questions. But on a more immediate level, as people are hiring, right? So today, nowadays, actually, if you look at the Seattle area, what's interesting is if you say you're a data scientist, right, you go to the tech companies, it's not trivial to get a job this year, at least for this year, it's not too trivial. However, if you go to utility and say, I'm a data scientist, you can actually pretty easily find a job for all the utilities we have. They are hiring. So people like Puget Sound Energy, Seattle City Light, GE Grid, which is housed here in Redmond, they're all trying to hire. Okay, so we'll see about why they want this kind of people. So not only utilities, for example, system operators are trying to hire data scientists, right? So this is a letter I got in my email about 2 days ago saying, we really want data scientists to know people, work on data science. So for those of you who don't know, ISO New England is the system operator for New England. So they are the people who run the power system for the New England 6 states in New England, right? So Massachusetts, Connecticut, Maine, and Rhode Island, and the 6 states. So they really want to hire people. Similarly, if you look at NREL as a national lab, this is the National Renewable Energy Lab. If you go to NREL, again, even though it's a renewable energy lab, it's a national lab, about 50% or 60% of their open positions has something to do with data and machine learning. Actually, even for national lab, right? So yeah, so what's interesting is if you look at, the people that have been graduated, I think from last year, or the trend has been, you go to the tech companies, you do data science, that's where you go. For this year, suddenly, these people went from not being able to hire anybody doing data science to, for this position, they got 100 resumes, but the complaint is 90 of them doesn't know what power is. Right? So that's where you do data science. This is sort of interesting trend we're seeing. Okay, so in this class, let's again try to see, one is this potentially you have this kind of jobs, and again, you have this kind of jobs, and they may open up some opportunities and give you a view of data science techniques that you may not see from other places. Right? Power system is a very particular system that has a lot of idiosyncrasies of how the system works. So show you how some of those show up when you study the sort of data science techniques. Right, and even if you look at tech company, again, so this has some folks in Google I work with. So this is Google X. And Google X is now very much into the electric grid. Google X has a team of about 60 people who's trying to make the grid better. I'm not convinced they know exactly what that means. Still, this is sort of big direction for everybody. Right? So now grid is going from something that power is something you take for granted, right? You say I flip the light switch, should be on. That's sort of basic utility to something nowadays that's actually becoming sort of more interesting to think about. Right? So it's sort of going from so something that you don't need to think about to something that we're sort of more cautiously thinking about. Okay, so any question about those, about what I talked about? All right, so so now it's for us to think a little bit about machine learning power system, right? So the one question is, machine learning power system is why? Why, do we need to do learning? Why not? Power systems has been around for, in the US, at least for 80 some years, right? But that didn't seem like we need learning before. So why are we now interested in learning in data science for power? Can you guys think of some applications? You want transfer, right? Basically electrons from one place to another. Why do you need machine learning to do this? Right, forecasting load, good. So one of the biggest uses for learning power system is actually load forecast. And so load forecasting means thinking about what the future load is. This is actually how the system works. So the way the power system works is we don't wait until this instant to determine how much generator should generate base load, right? So what we do is all the planning, all the sort of dispatch of the generators is done at least sort of a day ahead. Okay, so you have generators, things like nuclear, like coal, that takes a very long time to ramp up to do anything. So you need to tell these generators tens of hours ahead of time what their generation level should be. Okay, so for example, right now we're determining for tomorrow at 6 p.m. what should this hydro plant produce. Not obviously you need to forecast a load. We don't know what the load is for tomorrow. Right? So load forecasting is I guess sort of fundamental thing, the fundamental operation we do in power systems. So is this problem getting harder or easier for say today compared to the system, let's say 20 years ago? Why is it easier? Uh, Not necessarily, no. So what has changed in the power system in the last, say, 20 years? More renewables? Are renewables easier or harder to forecast? Right. So it's not necessarily it's harder to predict weather. Load forecasting very much depend on weather, right? So it's not necessarily that it depend on weather. As the renewables depend on weather much more sensitively than load. The renewable has a much more sensitive dependence than load. So this is harder problem. Okay, so renewables, things like wind and solar, is much harder to forecast than load. It's for order of magnitude actually more difficult to forecast than load. So to give you idea of this kind of things is, so let's say you have load forecasting without renewables. So this is basically just the electric load in the system. Let's say for Seattle, 24 hours ahead. Okay, so load forecasting, you're forecasting load for Seattle 24 hours ahead. What do you think the accuracy is for the load forecasting algorithm we're using now? Any ideas? What do you think, like how well can we estimate load? As the city of Seattle tomorrow at 6:30. Yeah, so how good? Any ideas, guesses? Sorry? No, yeah, so the accuracy or the error, we have about 1% error, actually. And you don't need a very fancy algorithm. You can run linear regression, okay, you about 2% error, actually for Seattle. Okay, so this is about 1% error. Let's say 2%, yeah. That's it's hard. Again, a linear regression based on temperature, time of day, day of the week, time of the year, and so on, will get you about 2% there. Okay, so this is not super difficult. How about wind? How about let's say now I have a wind turbine, right? I want to forecast how much power this turbine will produce. Again, wind turbine is not really controllable, right? It's not like a gas plant. You tell it how much to generate. Wind power is just however much wind it gets, it will forecast. How about wind power 24-hour ahead? So I can predict low to 2%. What is this? Any guesses? So this is about 30, if you can get this is 30% error, you have a very good algorithm. Okay, so state of art algorithm, depending on where this is, right? So if offshore, it's easier. But onshore wind, 30% is state of the art that you can do. Again, depending on the wind, exactly where the wind turbine is, but it's harder, this is much harder to do than forecasting load. Okay, so for this, linear regression will work. Linear regression does not work for this. Okay, you need sort of fancier algorithms to get this thing to work. Okay, and the reason there's physics behind this. The physics behind this is, if you think about your forecasting wind, right? So if you look at the weather forecast, it will tell you wind speed is about, say, 20 miles per hour coming out this direction. So we can forecast wind speed. There's some error within wind speed. But the relationship between wind speed to wind power is actually a cubic relationship. It's roughly the wind speed cubed. Okay, so this is for how kinetic energy works. So the reason it's cubed is the kinetic energy in wind is squared. The other sort of speed comes in as the more wind goes through an area, the more power you generate. So the speed times this area, so you have this sort of speed cubed relation that comes up, right? So now you have a 5% error here. You cube this. This is basically you're cubing the, you 3 times the air. This is essentially the air will accumulate in this. Okay, and this is just a wind speed to wind power forecast. This doesn't take into account the turbine, right? Do you have a sort of complicated turbine? Do you have a wind farm that each turbine impacts each other? Okay, so the whole forecasting problem is actually quite a bit harder than load forecasting for a city. In a city, what you have is basically you have this sort of central limit going on. That everybody behaves, essentially there's a lot of independent behavior. You sum it all up, and then you can sort of just look at the mean. It's sort of very well concentrated around the mean. For wind, you don't have something like that. Right? The speed gets cubed, and so this is already not super easy to forecast at a specific location. You have to cube this to get the air, right? So for wind, it's the same thing. You were looking at, for solar, it's the same thing. You're basically looking at, can you predict cloud cover at a very, again, specific area? Can you, do you know how much cloud is going through that area, right? So that's, again, much harder than forecasting low. And even low forecasting itself is becoming a lot more challenging. Because before, all the forecasting you do is you forecast for a big enough city. You just forecast for an entire city. Now for forecasting, we want to forecast to, for example, individual level. We want to forecast what happens for individual household. And so forecasting for sort of small customers is also much harder. Right? Because again, you don't have this sort of averaging effect. When you have a lot of people, this sort of just average out. And it doesn't really matter what individuals do. However, you're forecasting sort of for a small number of households, then it's much harder. Right? So before, for forecasting, we're basically just doing this. And again, you run the sort of the most basic regression. Actually, a lot of linear regression was first using load forecasting. There are journals on load forecasting that just do different regression. Now become much harder. Like wind forecasting, this is quite tricky. How do you forecast wind better? We actually don't quite know how to do this. All right, so load forecasting is a big area we'll do in this class. The first few weeks will be studying load forecasting. Because one is very relevant to power. Two is actually the easiest problem we can have. It's just a time series forecasting. You take all the input, you try to forecast what happens tomorrow. You don't need to really know all that much about the power system itself per se to do load forecasting. So that's where we will start the class. As we move along, we'll get sort of much harder, more problem that involves the system a bit load forecasting. Okay, good. So load forecasting is one problem, one type of problem we want to solve in power systems. Any other type of problems we want to solve in addition to load forecasting? You understand? Okay, so load forecasting is one. Another thing is that we tend to care about is fault. Right? So if we have a power system, the power system has faults all the time. Like some line gets disconnected all the time. The question is, can you predict this? Right, so right now, if you have a power outage, basically some line, you lose a line, then you figure that afterwards. People will call the utility saying, I have no power. Then you figure out where the line is and try to do something. So if you can proactively do, some fault prediction, that will be useful. If we know there's a storm coming, can we, be more predictive and where the power outage is likely to be? Right now, we just, the station crew somewhere and then wait until people call. So there's outage, right? So we try to be a little bit more proactive. Okay. Any questions about the fault? Okay, so this is one thing. I guess, so along load forecasting, can you think of something that's sort of similar to load forecasting, but not exactly trying to predict, let's say, tomorrow's load? Right, so what is being very hot right now, right? You have things like, ChatGPT, all this generative AI being extremely hot right now. So in power system, you also actually care about this sort of kind of generative process. And this shows up a lot in planning. Right, so planning is not necessarily you're forecasting what will happen. As when you build a power system, when you sort of trying to add something to the system, what you always ask is, if something happens, what do I need the system to do? Right? So a natural question you can ask is, suppose the temperature in Seattle on average goes up by 1 degree. What does my load look like? How is the load distributed? Should I do something about the system differently? You can ask a question of, suppose EV adoption grows from whatever it is now to 30% of all vehicles. What does the load look like that? Again, that will inform the physical assets you need in the system. Okay, so there's quite a bit of this sort of, again, asking a question, what if something, tell me what the load will look like. Okay? This is still a very hard process for us. Okay, so people have tried using all these things, asking these kind of questions. They don't give numbers. The problem with the generative AI you see nowadays, it doesn't give you a number. So really here is you really want a number to come out. If the electric vehicle adoption goes to 50%, tell me at all the feeders what the load will be. That's sort of the general question you try to ask in the power system context. Right? So it's related to load forecasting, right? You can use forecasting algorithms for planning, but now still we want sort of a little bit more flexible planning algorithms, generative. Questions about this? Yeah, go ahead. Yeah, to admire. What is the forecast itself? Like the value of, oh, well, what is the typical load for Seattle? Is that what you're asking? Okay. So Seattle, typical load for Seattle is about, let me think, about I'll say around 1 gigawatt. Not quite 1 gigawatt, but around 1 gigawatt. So close to 1 gigawatt. Yeah. Yeah. Right. So your error, so let's say you have a gigawatt load, your error is about 20 megawatt, right? So 2% of that. 20 megawatt, I mean, yeah. Yeah. So that's it. Other questions? Okay, good. So actually, so a good question for you guys is a gigawatt a large number or small number when we talk about power, right? So is a megawatt a very large number? So, okay, so what is the average per person power usage in the US? Like for each of us, on average, how much power do we use? Right, just, if you take the total power, the average power consumption in the US, divide by how many people there is, what is that number? It comes out to a very round number, actually. It's coming out to around 1 kilowatt. So that's a power usage. That's a power usage, right? So each hour we use 1 kilowatt hour of energy, but on average we use about kilowatt. Okay. So this is fairly typical. This room is actually pretty typical. So that thing is probably the thing that uses the most power. Right? So that projector is pretty powerful. That's more than a kilowatt of power. Each of your laptops, eventually you have to charge this. This thing charges about 200 watts. Now you account for the HVAC usage, the lighting, your phones, and this computer and all that. It's around about 1 kilowatt. Right? Electric power usage for each person. Right. So 1,000 people is about a megawatt. 1,000 is about a gigawatt. A gigawatt is not a huge unit in terms of power. So you have a large nuclear power plant. Nuclear power plant is about 4 gigawatt. Right? The state of California is about 50 gigawatt. Right? So these are the numbers we're thinking about. Right. So when I say the air is like if you have a 10 megawatt air in a city size of Seattle, that's actually a very small area. It's not a huge area. You won't really notice that. Okay. So that's where the scales of numbers you'll see. Right. So all this, right. So all this prediction depend on the scale of problem we're looking at. Right. So planning, right? So planning again, this has a lot again to do with climate change. As you really want to ask questions of if the temperature goes up like this, and the adoption of technology does this, show me the load. Okay, we're sort of pretty far away from doing this easily. Right, this is not so easy for us to do. Right, and then the last thing that we'll look at in this class, or we'll try to look at in this class is, not the last thing, but one more thing we'll look at in this class is uh, sort of learning the system. Okay, so you will think that we know what the system is, what the system looks like. Turns out not always. Okay, so if you think of the power system, it looks something like this, right? So you can think of what the system looks like as you have a big generator, right? That's generating power. Then what this goes to is this goes into a transmission network. So you have some generators that's generating power. That sort of goes into different substations. Okay. So does everybody know what a substation is? Who has no idea what substation? Right, this is actual stuff. So this is what you see under I-5, right? So if you go from campus to I-5, you see this sort of big fence off area with all those transformers and machines. That's a substation. That's a substation providing power for Northeast one, for Seattle, for this part of Seattle. This is Northeast Seattle. Right? So substation, this sort of big area fenced off. You have all these transformers, these sort of disks. That's a substation, right? So what do we know about the system? Of course, we know all the generators. This we know very well. Transmission lines we monitor. Each of the lines have a sensor telling you what the line is doing. This we know. We know all the substations. We sort of, again, each substation is sort of $1 billion of equipment in there. So we know all these things. These things are very expensive, so a very good idea what they do. And then you have, of course, your home, right? So these are the loads. This is our building load. The thing we don't know is we don't quite know what happens in between. We actually don't know the topology of this network. And not you, right? So we don't know the topology, we don't know the parameter on the lines, we don't know all that much. But how we connect from substation to the final load. So the reason is all these things are built in the 1960s. And the record is not terribly good. As there exist some pieces of paper, they may not be very up to date, we may have lost the record. But anyways, this network, this thing just used to work. So you didn't really need to think a lot about it. Nowadays, of course, because if you look at all the new devices that's coming in, EVs shows up here, storage shows up here, rooftop solar shows up here. Right? So we have a lot of interesting things going on here. We know what this is. We know, we don't know what happens afterward. So a lot of the attention on using data is actually figure out what the network looks like. Like out of the substation, how does the line actually go through each of the homes? And which home is connected to which one? All of this sort of basic information you think we should know, we actually don't know. And the reason is never matter. Like this, so for power, up until I say 5 years ago, all the excitement was here. This is very boring. Load is very boring. Generation is interesting. Nowadays, load is the most interesting part. Generators are old. This is interesting, but we don't know the network. Right? So, us in a month or so, we'll look at given data. How do you figure this out? How do you figure out, right? So, what is cheap? It's cheap to install sensors here. If you have electric vehicle, it is measuring power. So you know the voltage power, for example, here. You don't know what's going on here. You know some information here. So can you combine them to figure out what is going on in the middle? Can you learn about the physics, the physical network? Right? So that's a question that we'll look at. Okay, so, and the last thing we'll do in this class is sort of the operations. Right, so all of these is basically, these things are not called these things doesn't make decisions. Right? Load forecasting feeds into the decision-making problem. These things by itself doesn't make decisions. Right? So we'll look at operations as so in power system terms, when you make decisions, it's called the operational system. As if given the data, how do you directly make decisions based on this data? Yeah, so how do you operate a system if, let's say, you want to either the physics is too hard to work with or it's not available to you, how do you directly go from data to making decisions? Okay, so this is hopefully, we'll see, but hopefully we'll get to this point. Okay, so we'll start from load forecasting, again, just forecasting basically. This is essentially forecasting what happens in nature, but we have a lot of people. And then progressively we'll go through more and more specific power systems and get to the operation of the system. And so this is roughly our plan of the class. Any questions on this? Any other topics here? Okay, so while we're going through this, right, think about the project you want to do. Right? So think about different projects you want to do. Think about which of these topics you like to explore. Right, so let's actually, let's take a 5-minute break. Then at 6:50, we'll come back, we'll go resume the rest of the class. It's extremely challenging to get from first principles, right? So whenever first principle is hard, you sort of use data and do this kind of shit. It's just that today, a lot of things that's hard to do from first principles, then you have a lot more data. So it's not like we're doing something that's extremely different. It's just you're scaling everything up. Okay, so neural networks before was, in the 70s was 2 layers. Now, of course, you can train that in 3 minutes, right? So you think this thing, just bigger, you're solving bigger problems. Okay, questions on this? Okay, so right, so terminology basically data science. I got this from the lecture notes. Sort of people sort of make fun of what data science is. So for this class, basically you can think about what do we do, right? So here R is statistics, in Python machine learning, AI is PowerPoint, this kind of thing. So for this class, so if you look at data science does have a lot of statistics, right? So it has a lot of statistics in it. So data science, so if you really want to sort of study the field rigorously, you have statistics, you have probability, you have sort of optimization. And so of course, we're not going to cover these topics in any depth, right? So we're not going to say much about probability. Okay, so what we do is we'll just sort of identify the relevant problems, let's say in power system operations, and show what data science tool can be used. Okay, so all the things we're showing, there are underlying sort of fundamental principles in probability, in statistics, in all these kind of things. Just we don't have time. It's out of the scope of this class getting into it. Okay, so in all the techniques, we'll try to say, this is optimal, this is not optimal. Keeping in mind, if you go out and you work in with power energy or in most domains, there's some version of trial and error there. So you need to sort of know what are the relevant problems, can understand the techniques, and try different ones. Like a big thing you want to get out, maybe the most important thing if you can get out of this class is you want to understand the problems. You want to know how to Google to find a way to solve these problems. You want to know where to find the data, and then try things on your own. That's sort of probably the most important thing you want to be able to do after this class. You want to know what is the right thing to Google. Yes. You want to know what is the right data source to use. That's actually the most useful thing in this class. Okay, so in this class, we'll just give examples of how things are done. And we'll try to cover fundamentals if needed, but knowing that, again, we're not going to go very deep into any of these topics. Okay, so this is the terminology, right? So for us, is basically the way we think about the problem as we think of data science as, so what do we learn, right? So we have a box. Basically, we have data, we have some system knowledge, right? And as output, we want something that's sort of useful output. Okay? And so what we'll learn is we'll sort of learn, what are the right data you can use and where you can find the data. That's actually not trivial, right? So where you find the data, if you have system knowledge, how do you put it into this box? And then for different use cases, what are the different boxes you should use? Right? What are the different types of box you want to use for in different context? Okay, and again, anything in this class is not going to be exhaustive, right? So we're going to give you some examples. And the idea is, if you want to look at these things on your own, you should be able to, after this class, have enough knowledge to do things on your own. Any questions for this? Okay, so for example, this is not going to be a deep learning class. We'll do deep neural networks. For us, it's much more of this is how you call the command. This is what you put into it. This is what comes out. But we're not going to worry about exactly what goes on when you're trying to deep neural network. We just say this is something you can use. Right? This level will cover the tool. The more of look at different examples, problems, and understand what are the right tool to use for them. Okay, so right, so some example of the different tools, right? Example, this is again load forecasting. We start talking about this, right? So now this is example of load forecasting. Okay, so there's sort of different things you can look at. This is showing you the load, and this is showing basically the temperature dependence on the load. So PJM. So PJM is a very often used example we have in this class. PJM is the largest operating area system, largest system in the US. This mostly stands for Pennsylvania, Jersey, Maryland. PJM is much larger than this three states, but that's where sort of this all come from. Okay. So load forecasting, right? Temperature is a main feature. So this is high temperature, medium temperature, low temperature. This is different kind of load you have. And load forecasting is basically, let's say I cover this part. I give you these things. I give you some temperature forecast. Can you forecast the rest of the load? Right? Can you tell me what the load is? Okay, so given part of the load, given you know the temperature for tomorrow, can you tell me what the rest of the load looks like? Okay. So if you look at this curves, again, for the entire area, this is not very hard. Okay, you're aggregating, maybe this is probably close to 100 million people together. So you have this sort of very regular shape. Okay, so this tends to be an easier problem. But the idea is the same, right? So given some historical data, given something about tomorrow, for example, the temperature you know, forecast a load. Okay, so that's a basic load forecasting algorithm. And then these are the pictures showing the spread. So this is the error you make, right? So in this axis, this is the true data. This is the forecast data. So if they're in a line, that means they're doing a very good job forecasting. Okay, right? So if the true data is the same as the forecast data, x equal to y, you're on a line. Okay, so this thing, if you're forecasting 1 hour ahead, you're doing a very good job. Right? So essentially, you're getting everything exactly correct. As you look further ahead, more and more, your spread gets sort of larger and larger, right? So this is pretty large spread. Except when you get to 24 hours delay. Again, you get a pretty good spread. You're doing a pretty good forecast. Why is this? There's a very simple reason here. Right, so 1 hour is easy, 24 hours is easy, like 17 is not so easy. Right, so this kind of plot is saying the true data sometimes is here, like your data is here, right? So this is not a very good forecast. What is 24-hour easy? So look at those curves, right? Look at those traces. Why is 24-hour ahead easy? Right? It's not, well, it's linear everywhere. So it's mostly these things are oscillatory, but not super nonlinear. Like what distinguished, I said, between 17 hours ahead and 24 hours ahead? There's a very simple reason why. Right? What do you mean the data converge? Why does it more converge to the middle? I mean, 24, right? So this is a day ahead. Like, what is if you're going to do forecasting, what is the easiest forecasting algorithm? There's two forecasting algorithms. Let's say right now it's, what time is it? It's for 7, right? So 7, I want to predict what the load is for 8. There's two very easy algorithms. One is you see the load at 8 is the same as load at 7. It doesn't change all that much, right? It's very similar. Doesn't change drastically. Another thing you can say is the load for 8 today at 8 p.m. is the load for 8 p.m. yesterday. Right? There's a clear there's sort of daily cycle in all this load. Right? Every day at 8 a.m. is not 8 p.m. is not going to be super different. Right? So 24 hours basically you're taking off this daily cycle. 1 hour ahead, you're saying the load doesn't change all that much. Okay, right? So these are sort of particular to load forecasting, right? So if you're using historical data, right? If you have limited number of historical data you can use to predict the next hour, what should you do? You should use what is happening, right? 1 hour ahead and what happened day ahead. These are most related to what is going to happen next hour, right? We have this clear day-night cycle in the power system, right? So this tells you it's not that the longer you forecast, the harder the problem. You have to think a little bit about the sort of variation in load. Okay, right? So these are some of the idiosyncrasies, I guess, of this forecasting problem. In many other time series forecasting, it's sort of you want, just data as close to the forecasting time, or you want to say, the longer the harder it is, not for power. There's a very clear cycle in the power system that you should, one is you should leverage. Second, if you doing generative process, you want to generate for plausible looking load profiles, they better have this 24-hour period, right? So these are sort of the correct data, right? So load forecasting, again, is a little bit more complicated than just say, take everything and shove it into some algorithm, right? You need to make some choices. There's some choices you want to make here. Okay. Any questions for this example? Okay, so your homework again. So the homework in this course will, a lot of times ask you to explore this kind of thing. Right? Think about if you're designing an algorithm, what kind of data should you put into it? Okay? And so all the tools we're going to use in this class is a one-line function call. We're not going to make any new function. We're not going to build any new tool, right? We're going to do regression. It's one-line call. We call regression. We're going to train network. It's essentially a single line. You call train neural network, right? We're going to do SVM. It's still a single line. Okay, so all the actual tools you use, I think some sense trivial in this class. We're not going to go deep into the tool, right? Just a function call. So really what is going on is, what is the input, what is the output? What data do you input to the tool you want to use? What is the thing that looks reasonable for you when you get it as the output? Yeah, that's for this class, okay? And so load forecasting, again, a lot of things we cover, which is linear regression. Linear regression is literally a single line when you write the code. Okay, so most of the work is not calling that function. It is trying to understand, what's the right input, for example, of this kind of problem. Okay. Right. So there's load forecasting, right? So again, renewable forecasting is harder, right? So this is showing you what renewable things looks like, right? So this is, for example, a wind power that is generated through a week, right, or a few days, right? So you have a lot more peaks and valleys, and one, they vary a lot faster. Two, as you don't notice the patterns much. Okay, so when you do this kind of work, what is useful most of the time is just to plot whatever you want to forecast, right? You plot that thing, should be easier to forecast than this. Okay, so you want to plot, you want to look at the data, see what is reasonable, and so on. Right, so this another example. This is a little bit newer example. This is not this is realized because we have better measurements now. Okay, so for power systems, okay, so power systems, what happens is we used to measure the system every 4 seconds. Okay, so in power system, the standard measurement sampling period, you sample the system every 4 seconds. And you look at what's going on in the system. Right? So you have this sort of, you sample. There are many, many things that's faster than 4 seconds in the power system. In 4 seconds, your system may have blown up in some cases, right? So when people invented something called a phasor measurement unit, what these things do is you basically sample at a higher frequency. Okay, instead of sampling every 4 seconds, you build essentially a A to D converter that can sample high current and high power, high current and high voltage. This will sample at sometimes, half a hertz to a, so we'll sample at 30 hertz or sometimes at hundreds of hertz. We'll sample what is going on in the system. Okay, so we try to sort of do this very fast measurements to look at in the system. And the challenge that happens here is before when you sample every 4 seconds, you don't have that much data. So it's a relatively small amount of data. You can get the data, run the optimization problem in 4 seconds. Humans can actually look at the problem in 4 seconds. You can look at it fast enough. You can make a decision in 4 seconds. If you sample at this kind of rate, there's no way humans be able to tell anything at the 30 hertz. So basically, you have all this new data. Something has to process the data. Right? So something has to process the data and deal with all this new data that's coming in. Okay, so these are actually one challenge is now we have very fast measurement devices, and we don't know what to do with the data. This thing produces, I think in the Seattle area, this thing produces a terabyte of data every day. What we do most of the time is you just store it to some hard disk and put it in a warehouse. We have no idea what to do with the data. Right? So hopefully the idea is, can you think of more useful things to do with the data? Okay, so right, so again is you have, so the need for, going back to the need for data science machine learning is again, we have harder problems. We have a lot more data, right? So you look at every 2 seconds compared to several times AC cycle, you have orders of magnitude, 3, 4 orders of magnitude increase the amount of data you have. So algorithm that works for, every 2 to 4 seconds doesn't work if it's sub cycle. Okay? So we have questions that's really there's no physical based answers. Something like demand response. Demand response is if you pay people to reduce their power consumption, how will they respond to the signals or payments you're showing people? There is no physics there. All you have is data. You have what you tried. You can observe people's behavior and try to make some decisions there. And there's no physics. And really, the techniques are easier to use, right? So, 10 years ago, training a neural network is not trivial. It takes you at least a few weeks to write it. Nowadays, is one line of code. We can all do it, right? So the tools have become a lot easier to use, right? So part of this class is learning the tools. Part of the class is learning, what is the input and output to the tools. Okay, so demand response is an interesting problem. This is something that is an open problem on how to use data for demand response. Okay, so demand response is again, basically you get a signal to reduce your load, right? And you're given a reward based on, you're given some reward if you reacted to the signal, right? The challenge with demand response is often you don't know the counterfactual. As when you give people a signal, you know what they have done. But what you don't know is you don't know what they would have done without your signal. Right? Let's say I'm going to pay you $5 to reduce your load. Maybe you would have reduced the load no matter what, whether I paid you or not. Right? Maybe because I paid you money, you actually increase your load consumption. That can happen in practice. So this is a very tricky problem. It's because you don't know what would have happened. All you have is the observation. Under the fact that they received the signal, you need to figure out, how much load did they decrease? Did they actually decrease their usage? And so that's a that's a data science problem. That's not really a power engineering problem, right? So we'll look at some techniques later in the class to say, if you have ground truth, you can estimate something. If you don't have ground truth, you just observe what happens if you give something a treatment. How do you estimate how much this thing matters? Okay, so how do you estimate if you only see part of the data? You don't see the full data. Right, so faults in the system. And so again, as faults in the system, as we'll have right? So right now, the way that we trip lines in the system is we hard code everything. Okay, so right now, if you, for example, have a transmission line, if you have current flowing the line, your breaker will trip if your current is large enough. If your currents operate at the area that you think is abnormal. What we're seeing more and more is the following thing is if something goes like, system is fine, you have error, or you have operating at some place that sort of, there's a warning sign, but system looks fine again. But then later the system, you have an outage, even though you recover to the green operating point, everything is fine. Right? So this kind of thing is very hard to detect using hard-coded algorithms. This is challenging. So how do you come up with the more sophisticated algorithm can detect this kind of failures? And the reason is, so when there's high current, so actually this is an interesting thing about why we design this way. Let's say you have a line. Okay, so you have breakers on the line, right? Let's say you measure high current. Okay. So in your home, what happens if you measure high current? This breaker basically opens and the line just out. Okay. But in the power systems, we don't want to do that. You measure high current, it's not exactly we just take this line out. Can I think of a reason why? So let's say your transmission line, you have breakers, you measure high current. Your reaction is actually not immediately just kill the line and then wait for somebody to restore the line. So what typically causes high current in the system? I have a power system, I have a transmission line sitting there. What do you think is the most likely event that will cause high current? It's a natural event. What natural event gives you a lot of current? Right, but why? So you don't want the high current to pass through it because you don't want to heat up, right? But what can result in a lot of current flowing in a line? What is it? The lightning, right? Lightning strike. Lightning strike is by far the most likely cause of high current on the line. It's a metal wire suspending air, right? So if the lightning in the strike, it strikes that thing. Okay, so lightning strike happens, pretty common. The thing with lightning strike is once it strikes, it's done. Right? So lightning strike is not going to melt your line. Has a lot of current, but the current will pass away. Right? So the current will pass. So lightning strike can cause high current. A small animal getting here will cause high current. Again, happens more than you think. But those again are sort of one-time events. Right? So the way this thing works is if you measure high current, the line actually opens. The both sides will open if you measure high current. Then what happens after, let's say some time, let's say 0.5 seconds, both sides will actually try to close. Okay, so because the breakers doesn't know where there's a lightning strike, it just measures high current. So the default is you think it's a lightning strike, you open, you let that current, you don't pass the current through, but then you reclose. Lighting has finished, your line is still there. Okay, so this is the protection device as you go green, blue, green. The problem is that we're starting to see a lot more faults that this kind of sequential operation doesn't work. But we don't quite know what is the right way to operate this kind of equipment. That's actually a big issue with all this equipment. As we have a lot of hand design rules that made a lot of sense. But now because of renewables, because of, for example, EVs, this kind of thing, it's actually hard to keep working with hand design rules. And so you want some sort of more sophisticated rules that comes up. Okay. Questions about this kind of examples? Okay, so we'll cover the last thing we'll cover a little bit is, so we'll look at, what does data mean, right? So when we say data, there's sort of many things we mean by data, and we'll look at exactly what we mean. We'll give some very simple example of supervised learning and unsupervised learning, both happens. And this is pretty much the only thing we'll say about probability. It's either in this class or early next class. We'll say something about probability, then we'll be done with probability. So what does data mean, right? So data basically says, right, so there's, depending on, basically for us, it depends on how many variables you have, right? So right, for one variable, for example, load, you can get the data, you can look at, what is the mean of the load, right? So for one data, you can look at average, you can look at the average load, you can look at the variance of load in a day, those sort of things you want to look at. We can have, two variables, right? So this is, for example, the classical version of a two variable data problem is you look at global warming, right? You look at, or the temperature rise, I guess. As you can have one variable that's year, right? So year, no, that's years. The other one is temperature. If you plot these two, you'll see an increasing trend. You'll see, okay, as the temperature keeps, right? So in recent trend, temperature keeps going up. Okay, so we'll see a lot of that in power systems. One thing to be careful of is we'll be very careful when we draw something like a causal relationship. Okay, so you don't want to draw conclusions just because some things are related. You don't want to draw causal relationships. Okay, it's not enough to just plot x and y and see, oh, it looks like there's some trend. I'm going to say x cos y, or y cos x, or causal relationships. So be very, very careful when we draw causal relationships. A lot of times, if we have physical knowledge, we can draw causal relationships. A lot of times we don't want to. Drawing causal relationship a lot of times is wrong, right? It's not really causal. Okay, so for example, right, so global warming, now we think there's a causal relationship between carbon dioxide and the temperature. Can you think of something that will have a very clear relationship, but that's not causal? Okay, so there's a classical example. As if you look at people going to the hospital and death, those are very, very related. Okay, so you can, looking at who goes into the hospital, you can fairly reliably predict, this fraction of people will die. Of course, the causal relationship is not because of people going to the hospital, they're going to die, right? There's for a lot of common driving factors there. So again, drawing causal relationship, you want to be very careful. Okay, you don't want to draw causal relationship without some knowledge. And then if you go work for a company, actually, you'll spend most of the time arguing about this. Your boss really wants something causal. Did A cause B? Your job is to be very careful about those kind of things. Okay. And then we'll look at data, right? When you have, many, many variables, we'll basically divide part of the variable into the input, part of the variable into the output. Right? So we'll have a box. We'll have X coming in, we'll have Y coming out. And the important thing here, when we have many variables, is you don't want to use your prediction as an input. So sometimes you make this kind of mistake is you tend to use your prediction, you're peeking ahead in some sense, right? So we'll get to this when we cover it. We'll try to avoid, so we'll try to tell you sort of how to be careful when you have a lot of variables floating around. Be careful, what is input, what is output. Okay, so again, let's think about, we have a single variable, right? So a single variable means, let's say I want you to look at so for example, as the average load. So let's say in Seattle. So this says, you take 365 numbers, right? Every day you find a load and you look at it, there's some distribution of the load, right? There's some, does the load look like any of this distribution? Is there something particular about the load? Okay, so the way you do this is, again, of course, you get the load, you can plot all the histograms and you just look at it, right? And one of these. Okay. So if you do statistics, of course, you spend a lot of time thinking about this kind of distributions. For us, mostly you just take this and plot it and see what this is. Just look at it because it's always a good idea to plot your data, right? So it'd be interesting, if it looks geometric, this is very different than if they say the low looks normal. Right? It's just different things that it's good to know. But we're not going to say very much about how do you estimate this kind of probability distribution. And so for us, the probability distribution is take the load, just plot the histogram and see what is going on there. Okay. And the reason we don't do that, this is typically a two-step process. And so if you take probability, what really is if you take any crossing probability, this is your starting point. You have a distribution. You have to say something about this, right? This sort of random variable that has it. The problem with working with data, especially data in the power system domain, is what you have sort of raw data. Nobody will tell you it's uniform or it's Gaussian or something else. Basically, all you have is raw data coming in. To use this probability sort of way of thinking is, one, you have to think of which one of these really is the right distribution. You have to figure out the parameters associated with all of these. And then from that, you have to make some other inference. You have to say something about that distribution. And so that is actually very, or takes a lot of steps, becomes much harder if you have, for example, more than one random variable you have to think about. You have to think about correlations, all that becomes hard. So we are really not going to think about things this way. So for a lot of algorithms we'll cover, you prove optimality or you prove some theoretical foundation about the algorithm as you start thinking, you say, if this has a normal distribution, then whatever happens. For us, we're going to just assume that algorithm works and try it out. And knowing that if you really want to be rigorous, this is where you go to be more rigorous. Okay, any questions here? Okay, so we'll care only about one distribution in this class. Okay, so the single distribution that we'll care about is the Gaussian distribution. Okay, so Gaussian is by far the most common distribution you'll ever see. Almost everything, if you read academic papers, most things about probability or this kind of thing starts with assume something is Gaussian, right? And so for who has not seen Gaussian distribution before? Everybody at least seen Gaussian, right? The PDF for Gaussian. Okay, so we're going to cover this sort of very quickly, and then we'll stop after we give the Gaussian distribution, right? The reason we care about this is we talk about some algorithm. Let's say we're trying to find the mean of something. You may just well assume the thing is Gaussian and think about the mean that way. Saying to find the variance of something, we just assume the thing is variance of a Gaussian distribution, right? Just think about things that way. Okay. So Gaussian does show up in some physical process, right? So for example, this is thermal noise. Right? So if you look at thermal noise, this is Gaussian. Another very important part is the sum of a large number right? So if you sum up many things together, you tend to get a Gaussian distribution, right? This is why if you look at the load distribution of, again, the city of Seattle, will seem sort of roughly normal in shape, just because you're summing so many people up, right? Summing so many people up. Okay. So again, even if things are not Gaussian, it's very useful to think about it as Gaussian, right? So Gaussian has two parameters, as a mean and a variance, right? Mu and sigma squared. As a mean and variance as its parameters. And then what you have is you have a distribution f of x e to the okay, so this is just our normal distribution that we have. And so again, I'm assuming we all seen this before. Well, we all seen at least this function before. Is this new to people? So who has not seen this before? Okay, so have you guys taken probability before? Right. Okay, so this is the PDF, right? This is probability density function of a Gaussian random variable. So what this does is, so if you draw this function out, this is just right. So this is centered mu, and then the function spreads out like this. This is for sigma squared, right? So this is roughly telling you sort of what is the probability density of x here. So what is probability density? How likely is am I, if I'm randomly picking some number based on this distribution, what is the probability of picking x? What is the density of picking x according to this distribution? Right? So this is what Gaussian is. Right? So if you look at, for example, if, I'm going to make up an example, load. The loading a city typically, let's say, looks something like this. Right? You have a mean load. Let's say this is 100 megawatt. And let's say you have a standard deviation of 10 megawatts, right? So this tells you on average, your load is 100 megawatt. And then how far does the load spread around this average? Well, that's what the standard deviation tells you. Okay, so this is what the distribution means, right? Gaussian distribution means. You can think of this sort of, you can think of this process, let's say the load in a average size city, average size town, as you're sort of randomly picking numbers along this curve. The higher the curve, the more likely to pick this number. And this is sort of what Gaussian distribution is in here. Okay. Right, so this is this Gaussian distribution. And the reason we care about this is the simplest data science problem is the following. I give you a bunch of data. Tell me the mean of this data. Right? Tell me what is the average of all this data I give you. I give you the load for Seattle for a year. Tell me the average load. Right? So that is very simple. That's extremely simple. That is, you take all the numbers, you divide by number of days, right? Based on that, you can now ask the question is, tell me the standard deviation. Tell me how spread out this load are. Are the loads similar to the mean, or are they very different than the mean? That is given by this sort of sigma, this variance. This variance will tell you how spread out the load is. Okay, so that's the idea we have for this kind of problems. And again, instead of thinking the mean and the variance abstractly, sort of just think of everything actually coming from Gaussian. You're observing a lot of numbers coming out of Gaussian distribution. How do you estimate the variance? How do you estimate the mean? And how good are these estimators? Most of the time you think about those linear distributions. Okay. So if you've never seen this, it's okay. We'll see this sort of the simple concept enough in here and in your homework. Is that this is sort of the only distribution we'll ever draw. That's for Gaussian distribution. Okay. Any questions? Okay, so this is Gaussian, and again, why Gaussian is this sort of, the good thing about this is parameterized by two numbers. Mu and sigma. Right? So the mean and the variance. And this happens to be really sort of the thing that's easiest to describe. right? So mean variance is how we think about randomness, right? What is the average of something? What is the deviation away from the average? That's a variance, right? So this is really how we think about how we think about data, how we think about the problem, right? So and the Gaussian turns out to be such a distribution characterized by the mean and the variance explicitly. Right? So there's a term that shows up as a mean. There's certain the mean shows up as in the distribution, variance shows up in the distribution. Okay, so that's why it's a very, very nice thing to work with. Right, and then again, the question we can ask once you think about this kind of distribution is, for example, as you can, given data, you can try to fit a distribution onto it. Right, so this is what, something called model-based learning. As you have all this data, this, for example, a Gaussian distribution, you can try to fit a distribution onto this. You can compute its mean, compute its variance, and then you can, ask different questions once you compute the mean and variance. Okay. And so we'll see this a lot more. So this just gives you a basic idea of what we'll do. You'll see more example of this actually later in the class. Okay, so this is the simplest problem is, again, imagine this is a load somewhere, and you ask, given this histogram, you plot all the occurrence of the load, can you estimate the mean and variance? Can you tell me what is the on average what happens? Okay, any questions? All right, okay, so if no questions, actually, let's stop here for today. We'll stop a little bit earlier for today because next we'll get into a lot of power system sort of background, and I want to do that sort of in one class. I'll do that in one setting instead of doing in two different classes. So let's stop here for today. The homework will be out tomorrow, so I'll post the homework tomorrow. Again, it will be very simple homework, asking you to do some sort of basic calculations, remind you a little bit of math. And the main thing is get the Jupyter Hub working. That's the main idea of that homework. Okay. All right. So thanks, guys. So any questions? Probably a week. Think of a week. Yeah. So maybe not a week. Let's say it'll be out tomorrow. Maybe do the Thursday after to give you a chance to ask question on Monday. Ask question today. I'll give you some time to do the homework. Okay. Okay. So for homework again, please don't copy each other. Right. Again, for this time we're using the hub. I have access to whatever you do there. I see your history. I see what you're doing. So if I look at your history, magically your code showed up by copy pasting everything. I see that. Okay, all right. I see. I have full visibility of whatever you're doing. So please don't do those things. Okay, right. And all these things are not very hard. It's sort of very easy. Questions that'll be useful for you. Okay, so good for homeworks. You can ask people. That's fine. Discussion is definitely fine. Just don't copy paste. Okay, so the reason I think UWIT set it up is they have very robust detection software for if people are copying with the same class. They do sort of automatic detection of all the code there. Okay, so so tomorrow you'll see the environment and just get it working, and I'll start with sort of some basic questions there. Yeah. Homework will be based on lecture and ask you to explore things. Homework will be based on the lecture, for example. Next time we cover linear regression, we'll say, okay, this is a new data set, do linear regression on this. Right. Or we'll give you some challenges of, this data set that linear regression may not work so well. Ask you do this and observe why it doesn't work and how you can improve this kind of thing. So most of the fundamentals principles will be based on lecture, but it'll be a lot of trying different kind of stuff using different command. Okay, so it'll be quite you need to Google quite a bit to do the homework, right? So you need to look at different commands. Right? I don't remember them, right? So you need to look at at least how the different commands for different kind of things. That at least you need to look at. Yeah. Okay, right. So if you have trouble, again, communicate with me. Very often. This is a very small class. So it's not like, we necessarily need a tier or anything, right? So just willing to travel, just communicate. Okay. Okay, thanks guys.